Well, thank you all of you for being here. And so I'm really enjoying this conference. So I'm really happy to be here and to have the opportunity to talk about this work. This is a work in progress in a very early stage with Kevin Peterman. And it's about the idea of trying to infer the fundamental group of a point cloud, or to infer the fundamental group of a topological space from a point cloud. So, now it's working. Well, so the main motivation in topological inference, you have seen a couple of talks about this. So you have a sample, and it's you think about it as a noisy sample of an unknown topological space. In applications, these points are data points. And the idea is to try to describe algorithmic tools to try to infer topological properties from the underlying space from the sample. And the main idea, or the crucial concept in this task of trying to infer these topological properties is the notion of persistence. So in general, you have your points, and perhaps not always you have some idea of how to measure distances between the points. In our examples, this will be the case, but it's not mandatory. And well, so instead of trying to reconstruct a single simplification complex or a guess of which is the underlying space, you construct a filtration of complexes. There are a couple of talks before they show some methods to construct the filtration of simplification complexes or CW complexes or complexes in general. And the idea is to try to so apply your favorite topological invariant and try to understand how these topological invariants it evolves along all the levels of your filtration. So you're not only interested in each level of the filtration, but also in how this invariant moves or change from one level to the other. And so you're interested in this notion of persistent invariance. So if you look at two different levels, you look at the image of this invariant under the induced morphisms that you have in another level of the filtration. And the most famous and very first example of this pipeline is persistent homology. And well, in this case, we are when we use coefficients in a field, we're very lucky because we have this nice structure of graded module, and we have the theorem that allows us to decompose both all these groups and also morphisms. We have all this information together in this decomposition that allows us to interpret this graded module as a set of intervals, as we have seen in many talks. So we have for persistent homology an algorithm that it's very similar to the computation of the regular homology of a simplification complex. And we have this, well, if you compute homology at degree D, perhaps, well, you can improve this with the, but in general, we can say that it's cubical in the number of simplices of dimension D+1. If you want to, in the biggest complex in your filtration, if you want to compute homology at degree D, you can improve it because you can compute multiplication of matrices more efficiently, but well, let's say it's cubical. The point is that we have an algorithm. So we not only, I mean, we cannot apply this pipeline in any for any topological environment in theory, but in practice for homology, we'll have this nice algorithm. Well, other side. Great. So here is a very simple example. This is a point cloud of just very few points in R3, and suppose that you can measure distances between these points with the Euclidean distance, using the Euclidean distance in the ambient space. And suppose that you compute the victorious filtration this filtration, you have a parameter alpha. So the set of vertices in every simplex is always the same. And then you have a simplex every time the diameter of this subset of points is less or equal than alpha, okay? So for different values of alpha, you have this filtration of these different complexes. And, sorry, and if you compute the barcode, so of course this is a very small example, but you can capture if you look at the long words, you can capture the homology of these well-shaped spheres. Okay, so you have a long var in H0, one long var for H2, and two long var for H1. Suppose that you consider this other example. This is a grid in R2, but I identify the points in the boundary of the grid, like in a torus. So we can infer from here a metric space. So here you have this identification. So there are small names in the vertices. And if you apply the same kind of computation, we have again the Vittor's grid filtration. In this case, we have a couple of have more points, but again, if you look at the long bars, we have again one generator in H0, two generators in H1, and one generator in H2. So what I want to say or motivate is that, of course, when you compute persistent homology, you have the same limitations as in the regular case. When you compute homology, you cannot distinguish between any pair of topological spaces with different homotopy types, because well, in these two examples, they have the same homology, right? So, sorry. Okay, so this motivates the idea of trying to compute the persistent fundamental group. So, from a theoretical point of view, the idea was just apply pi1 at every level of the filtration. You have an induced morphism, but what about a computation or a description of all these groups and both groups and morphisms? So I want to show you here a very simple way to compute or to describe the fundamental group of a CW complex. Suppose that it's of dimension 2. In other case, you just restrict to dimension 2. And well, so first step, you identify a spanning tree in the one skeleton, which is depicted in blue here. And well, so you can obtain this presentation that is known as the standard presentation associated to the complex. So you have a generator for each cell of dimension 1 that is not in the tree, and you have a relator describing the attaching map of the two cells. But here, if T is the tree, you think that it's a complex. You're looking at the presentation of the fundamental group of K over T. So if you collapse the tree in a point, then you have this complex with single vertex. So it's very easy to compute the the fundamental group, for instance. So here, of course, you need to choose some orientation. So here, for instance, you have this orientation. Well, this is example of the touching map of these two cells. As you can see, these kind of presentations are quite big because you have one related for each, almost for each one cell and related for each two cells. But anyway, so let's try it at least. So suppose that we use this pipeline in the computation of this persistent fundamental group. So if suppose that your complexes are connected, all the complexes in your filtration, to avoid these technicalities related to the base points, and the set of vertices is constant, okay? Like in the case of the Vittor's grid filtration. So you choose, you pick some tree in the first complex, and you spanning tree, and you can use the same tree for all the complexes. And then you compute this presentation, and you can see that, well, so of course, it's not necessary to apply the previous computation. So to repeat the computation for every level of the filtration, because so if you compute the presentation for the biggest complex, then so the one cells that does not belong to the same tree are the generators. You have the relators associated to the two cells, and every level of the complex you have less number of cells. So you have a subset of cells, a subset of one cell and two cells. So just restricting the set of one cells and the relators associated with two cells, you have these inclusions of relators and generators. So the morphisms are very easy to deduce. The problem is that, well, these representations are huge. I mean, they depend on the description of the complex in terms of one cell and two cells, and in general are a lot. So why? So the idea is to try to use discrete Morse theory to obtain efficient description of the composition of the complexes at each level of the filtration before computing the presentation of the fundamental root, right? Well, so more theory appears in a couple of talks as well. So the idea is to simplify the composition of the complex while preserving the homotopy type. In this case, we're going to think that our complex is a regular complex, but well, you can think of a simplicial complex. Let me recall briefly the idea of theory. So you have a discrete Morse function that is a labeling on the cells that satisfies this condition that every time you look at the value of some cell and look at the faces and cofaces, so the value of F increase with dimension with at most one exception. So you can classify the cells in terms in cells in which this value is equal to 0 or equal to 1. In the case in which this value is equal to 1, the cells comes in pairs. And in the case in which this previous number of when you don't have exceptions, so when the value of F increases with dimension, these cells are the critical cells. So here you have in the picture the critical cells in orange. And the main theorem says that, well, you have this decomposition, new decomposition of a new complex. I call it, we did KM in terms of the critical cells. The problem is that in general, so, well, why I am interested in this complex is because you preserve, of course, the fundamental group. And well, the problem is that in general, you don't have a complete description of the attaching maps. So you need to deduce it. And in particular, the attaching maps are very important for us in the computation of the fundamental group, right? Because they determine the relators. Well, in this case, we are not sure in principle, which is the fundamental group. So let's try to understand the idea of the proof of discrete Morse, of this main theorem, in order to try to reconstruct the attaching map of the two cells. So you have this notion of levels of complex, that is the subcomplex of the main complex of closed cells at which the value of F is less or equal than some specific value. So this is the sequence of levels of complexes. And you have two cases. First case, you go through a critical cells, you change the homotopy type, or you go through non-critical cells that comes in pairs and induce a collapse. But if you want to think all this idea together, you have this collapse, but it's obstructed by this critical cell. If you want to perform this collapse without removing it. So this is the idea of internal collapse. So suppose that you have a collapse, but you're touching new cell, so you cannot perform the collapse. This is this cell in red plays a role of the critical cell, right? And these collapses are the non-critical cells. So well, you can compute a new attaching map for this cell using the retraction induced by the collapse. So you have a new attaching map, and the question is, how are these two complexes related to each other? Well, they are homology equivalent. It's not difficult to prove. So you have this collapse, you perform this collapse internally, and well, this is a very simple case, but in general, you have many cells that are attached. So you have many other cells that are attached. These are critical cells, and you have perhaps here many other collapses. So the idea is to try to try to reproduce this simple procedure for all the critical cells and for all the internal collapse that you have that are induced by this sequence of levels of complexes. Well, it's possible to do that. So, you can write the main theorem in Morse theory, saying that, well, if you have a discrete Morse function, then you have this sequence of levels of complexes, and at each time you have either a collapse or the attachment of critical cells, of new cells. Okay, so either you have a collapse or new cells that you attach. And what all these process can be interpreted as a sequence of internal collapses that can be performed in order to obtain this Morse complex. And there is some way to try to track the attaching map of these maps. Right. Okay, so you have some sort of formula, but in terms of an algorithmic procedure, how to concretely compute them, at least in the case of dimension 2. So here's an example of, instead of computing the levels of complexes, you just perform, so this is the idea of the internal collapse. You perform this collapse internally, so you modify this attaching map, and then you perform this internal collapse and you modify the attaching map of the two cell that is critical until you obtain this the Morse complex. Yeah. Okay. And right. So are there any questions so far? Okay. Great. So so this is the presentation of the the original presentation that we used to have using a tree. But if we compute K plus a Morse function, and we compute, so we have, this is a representation in terms of these pairs of cells that are induced by the Morse discrete Morse function. So if you compute the Morse complex, and then you compute the presentation of the fundamental group, this is a presentation that you obtain. This is a presentation associated to this complex, right? So if you are allowed to compute the attaching maps of the two cells, then you can obtain this very small representation of pi1, okay? If you want to perform this algorithmically, so I coded some algorithm. So you give me a regular complex and give me a Morse function, and I asked the Morse function to have a single critical cell of dimension 0. This is for some. It's always possible to obtain this kind of Morse functions, and then I give you the presentation of the standard presentation of the Morse complex. Okay, and the complexity is quadratical in the number of cells of the complex. And I think that I'm going to show you an example. Well, for those of you that didn't work with Morse theory, so when you have a Morse function, it induces a matching in the set of cells. So in the case of dimension 2, this matching can pair cells of dimension 0 and 1 or 1 or 2. Okay. If you look at this at the cells, a pair of cells of dimension 0 and 1, then this induces a spanning tree. So since we asked the Morse function to have a single cell of single critical cell of dimension 0, the rest of the vertices and are paired with some one cell. So if you look at the non-critical cells of dimension, if you look at the non-critical cells of dimension 1, if you look at the cells that are pairs of cells of dimension 0 and 1, then this one cell determines a spanning tree, and this spanning tree can be used to is used in this algorithm. And then every time you have a pair of critical non-critical cells of dimension 1 and 2, then they induce some sort of rewriting in the touching map of the two cells. Okay? And something that will be important after is that you can perform these internal collapses of the two sets in any order. So you have this set of pairs of one cells and two cells that determines an internal collapse, and you can perform it in any order. It's the same, you're going to obtain the same complex. This is a consequence of if you think a Morse function as an acyclic matching, this acyclicity implies that any order is a valid order. So here's the example of how to compute the presentation of the standard presentation of the Morse complex associated to this original complex with this Morse function that is here. The Morse function is depicted as arrows between the cells that are paired. So first step is to so you have the tree used by the pairs of cells that are matching dimension 0 and 1. You have the tree. You compute this big presentation. This is the first presentation that we had before. And then every time you have this, you identify some internal collapse, any, and then this internal collapse here is associated to this one cell and these two cells. And then you apply some rewriting rule that is basically you write X13 as the rest of the word in the relator, and then you replace this relator X13 by this word in the rest of the relators, and then you eliminate, this is a collapse, you eliminate this pair of one cell and two cells, or this relator, generator and relator. So at this point, we have the fundamental group of this complex. And then we repeat this procedure. We identify this pair of cells, and then we identify the one cell and two cell in the presentation, and we rewrite this relator in terms of the rest of the world, and we iterate. So this until you perform all the internal collapses and you obtain this presentation. Sorry about all these presentations, but they are going to be important in a minute. Well, this is a description of how to perform this procedure. And the idea is that if you perform this procedure, this is the idea of the algorithm. This presentation that you obtain performing this procedure is the standard presentation of the Morse complex. Great, so let's try to apply this idea to the computation of the persistent fundamental. Now, we have a couple of problems. First problem is that, well, suppose that you have a Morse function in the biggest complex. If you restrict this function in all intermediate complexes, you still have a Morse function. Okay, great. So we're going to try to make this procedure in a coherent way. So we use the same Morse function restricted. But when you compute the Morse complex at each level, you lose the property of being this filtration. So you don't have inclusions, not necessarily. Then so how to infer the morphisms? Other problem is that, of course, so you have this algorithm to compute pi1 of the Morse complex at each level, but you cannot do it, repeat it for every level of the filtration, right? So how to make this computation more efficiently. So the good news is that you can do, so the same algorithm that I showed you before, if you apply this algorithm to the biggest complex, then there is some way to, so you have the presentation of the most complex of the biggest complex, and there's some way to deduce all the presentations. So you apply the algorithm once, and then you can deduce all the intermediate presentations. And also you can deduce all the morphisms connecting all these presentations. And well, you have this commutative diagram. So it's another way to compute this row. And let me show you how this works in this example. So suppose that this is your filtration. So you have this complex. This is the complex in our previous example. And these are other intermediate complexes. So you run your algorithm once, and then you have all these intermediate presentations, and this is a presentation associated to the most complex associated to the biggest complex. And then let's try to deduce all the intermediate presentations. So for the first one, you need to identify the first time you have performed, something that is important. You choose to perform the internal collapses in some order that is consistent with the filtration, okay? So you perform the internal collapses that are present in the first complex of the filtration, and then the others, okay? So this is not a restriction in the Morse function. I mean, you have these internal collapses, and then you have your filtration, and you choose the order in terms of the filtration, but you can use any Morse function. Okay, so you look at the first time you have performed all these internal collapses, this intermediate presentation, this one, and then, of course, this presentation uses cells of the biggest complex. So you have to, if you want to compute the presentation associated to this complex, you have to intersect these relators with the ones that are present in this complex, and then you have to intersect. I mean, you have to choose only the cells, so the relators that are related to cells that are present in this complex, and you obtain this presentation. So it's sort of intersection of this presentation with the cells that are present in this intermediate complex. For this other complex, again, you look at the first time you have performed all the internal collapses, and then you have this presentation, you have already computed this presentation, and then you intersect the cells or the relators, and then you intersect the relators. And finally, of course, this is a presentation associated to this complex. This is the toy example, so perhaps this filtration is just I know it's just a fake filtration that I used to show the algorithm. And well, so this is the statement that says how to compute all this intermediate presentation. So you have a complex that is filtrated. So you say which cell is at each level of the filtration, and this number is the first time. So you have all these intermediate family, all these presentations associated to the computation of the presentation of the biggest complex, and then you can deduce all the intermediate presentations. So you have to run this algorithm just once. And also, sorry for this slide, but you can look at it online, but the idea is that how about the morphisms? Well, the morphisms can be deduced in terms of these rewriting rules, right? So you compute the composition of these rewriting rules. So to obtain one presentation and the other, you apply the rewriting rule, this rewriting. So there is some formula to compute the composition of some of these rewritings. And you have this commutative diagram. So here you have the original computation of the presentation using the tree, and here you have this the presentation using this Morse function. Great, so you can look at this slide after. And in this example, so it's very small because I run this computation by hand. So this is the these are the filtrations, and I put with some small arrows here the Morse function, sorry, or the magic. And then if you if the complex, this is the Vittori's filtration, so if it's not connected, I'm not going to use this level of the filtration. Since these complexes are connected for the value of alpha equal to 1, I compute. So I run this algorithm, and you have, so here you have in the bottom the description of the fundamental group, of the presentation of the fundamental group using this algorithm. And here is a description of the morphism. So here you have many generators because it's free in some number of generators, and here you have just 2 generators and the relation associated to the fundamental group of the torus. And so if you compare with the barcode, so here you can combine. So here you have the free group into generators, and it's associated to these 2 bars, so to this interval. And here, so you have here many generators, and in particular, these 2 are also here. So here you have presentation of cell times cell and correspond to this part. But so 2 of them are also previous. So in the previous interval. So so again, this is a project that is in an early stage. So so I have many things to still think about. In particular, how to combine all this information with information of persistent homology. We're implementing this algorithm in GAP. That is software that is very efficient for group computations, and to try it in real data sets, in bigger data sets. Well, here's some references, and thank you for your attention.
Questions from the audience?
What do they say this barcode in the case of fundamental group? Because I understand in persistent homology that you can really compute it, no? It's really hard. But here, the fundamental group, you don't even know if it's free or not.
No, you just have presentations here. Yeah, so you just have presentations. But what we are thinking is in some sort of, so the idea is to, let me put back. So the idea is to try to distinguish between, for instance, here, when you abelianize the fundamental group, you obtain the same homology. But perhaps, so I know that this is something that we have to do. If you have just the relators and generators, it's difficult to say which is what does it mean. But we're trying to at least identify in some cases if you can detect that some bars correspond perhaps to if the fundamental group is not abelian. So I don't need the exact description perhaps of the fundamental group, but if you can distinguish in some cases, this is the same problem that you have when you compute, when you obtain a description of the fundamental group in terms of representation. So you have this, you inherit the same problems as in the regular, in the case of topological spaces. It's hard to understand or to compute explicitly there. It's impossible to compute the group. Yes, so we're trying to extract from this group some sort of invariants, like for instance, the fundamental group is not abelian for all these for these intervals, so you can combine it with persistent homology and say something. Yeah. So this is like the raw all the information. This is too much. This is you cannot manage all this information still, but yes, so the idea is to process, to make some processing of some additional step to this set of groups and automorphisms to identify something that is some property of the group that is persisting along some interval that is different perhaps in some other examples, so you can explain.
But my feeling is that there are two independent problems. One is that from the presentation, you cannot tell two presentations of the same fundamental group. So from the presentation, you cannot tell whether you computed something else or the same. But the bars, you draw these bars and you speak about these bars, but I really do not see how you get these bars.
No, sorry. These are the bars of the persistent homology. So I'm just combining this information that is independent from this other. No, this is not a representation of no. No, the idea is to combine these two informations.
More questions? Okay, let's start the speaker then. Here. Who is given the next?
So thanks for this nice talk. I just want to
Yes, wait a second, first, second.
We feel like I'm tried to go